Hello everyone and welcome to my talk. First of all, I'd like to thank Julie for organizing this festival and for the great opportunity of participating in it. So my talk will be about geometric flows of balanced metrics on almost abelian Lie groups, and it is part of a recent joint work with Anna Fino, which is currently on the archive. And just a few words about the structure of my talk. So first of all, I'll review some preliminary notions about complex geometry and Hermitian geometry, including the definition of balanced Hermitian metrics. Then I will present some of the main properties of two of the most important geometric flows in balanced geometry, namely the so-called balanced flow of Bedulli and Vezzoni and the anomaly flow of Fohm, Picard, and Zhang. To end this talk, I will spend a few words about the results I have obtained with Anna Fino regarding almost abelian Lie groups. So I will review some of the known facts about Hermitian geometry on them, and then speak about the behavior of the two aforementioned flows on almost abelian Lie groups. So, as I said, I first want to spend some time on preliminary notions so that we are on the same page. So, first, a definition. A complex manifold is a smooth manifold submitting a holomorphic atlas. So, first of all, we have to assume that our manifold has even real dimensions, so that R2n can be identified with Cn. And so a natural thing we can do is demand that the transition functions of our smooth manifolds are actually holomorphic functions between two copies of Cn. The atlas is considered as fixed, since different atlases may give rise to possibly non-equivalent complex structures, the same thing that happens with the smooth manifolds, where different smooth atlases can give rise to different differentiable structures. And one thing one can notice is that given that the transition functions are holomorphic, we have a well-defined linear endomorphism of the tangent bundle, which we call J, which squares to minus the identity. And this is simply obtained by identifying locally J with the multiplication by I. So the question one can ask is this endomorphism all we need to have a complex structure? So does it suffice to have an endomorphism of a tangent bundle that squares to minus identity to have a complex structure on M? This is not always the case. So naturally we can relax the hypothesis of a complex structure by defining an almost complex structure, which is simply a linear endomorphism of the tangent bundle of a smooth real manifold which squares to minus the identity. Once we have this, we have a natural decomposition of the complexification of the tangent bundle into the direct sum of its eigenbundles with respect to the eigenvalues I and minus I. This decomposition induces a decomposition of the complexification of the bundles of exterior forms in this way. So, as I said, having an almost complex structure is weaker than having a complex structure. So what we are missing to bridge the gap is this theorem, which takes the name of Nylander and Nirenberg, which says that an almost complex structure J comes from a holomorphic atlas. In this case, we say that J is integrable, if and only if one of these two equivalent conditions holds. The former is that T10 is involutive with respect to the Lie bracket on M. The latter is that the neo-noise tensor associated with J identically vanishes. So, in this case, we have that the round differential D splits into the sum of two operators called D and D bar. Now we also want to speak about Riemannian geometry in the context of complex geometry. So we say that a Riemannian metric G on an almost complex manifold Mj is Hermitian if J is orthogonal with respect to G. The associated fundamental form is the true form which is defined in this way, you can see. And in this case, the previous condition ensures that this is actually skew symmetric, so that it is a true form. and in what comes next, we will usually identify G and omega. So when we have an almost Hermitian manifold, we say that a linear connection is a Hermitian if and only if it preserves both the complex structure and the Hermitian metric. Godushan in 1997 showed that an almost Hermitian manifold always admits a line of Hermitian connections, which are parameterized by this parameter tau. There are some important connections in this family, which are the bismuth connection and the Chern connection, corresponding to tau being equal to -1 and 1, respectively. So, now that we have said what an almost Hermitian structure is, we can talk about some special almost Hermitian structure. So we say that an almost Hermitian structure, Jg, is scalar, if and only if its fundamental form is closed and J is integrable. Scalar structures are the ideal Hermitian structures because in the Kähler case many beautiful things happen. First of all, we have that the Levi-Civita connection is actually a Hermitian, so that J is preserved by the Levi-Civita connection, and actually the whole Godushan line we have defined earlier collapses to the Levi-Civita connection. We also have that the holonomy group of a Kähler metric is contained in the unitary group, and that there exist local normal homomorphic coordinates around any point in which G is standard in a suitable sense up to the second order. One of the most important things is that in the Kähler case, the fundamental form provides a symplectic structure, so that we have a very nice interplay between three different structures on the same manifold. These structures are a metric structure, a complex structure, and a symplectic structure. This interplay between them is also made more clear by the Kähler identities. Having a Kähler metric implies very strong properties on the smooth and complex structure on the underlying manifold. For example, we have some constraints on the Betti number, which are the dimension of the cohomology groups of the manifold. Then, speaking about the complex structure, we have the Didi-Bar lemma, which in particular says that in this case, a Kähler metric is determined locally by just one single function, which takes the name of Kähler potential. And we also have that the exterior bundle with the round differential is formal in a suitable sense. So, a question one might ask is the following. Given a compact complex manifold which admits Kähler metric, can we find the best Kähler metric on it? First of all, we have to agree on what we mean by best Kähler metric. One possibility is requiring that the Kähler metric is Ricci flat, and this is exactly the content of the famous Calabi-Yau theorem, which gives an existence and uniqueness result for Ricci flat metrics on a compact complex manifold with vanishing first-Chern class. The vanishing in the first-Chern class is a topological requirement that is needed to admit a Ricci flat metric. Now, weaker conditions have been studied. For example, the Kähler-Einstein condition, the constant scalar curvature Kähler condition, and finally the extremal Kähler metric condition. Extremal Kähler metrics in particular can be seen as critical points of the Calabi energy, which is the functional you can see, which takes a Kähler metric and gives the square of the L2 norm of its associated scalar curvature. So, just a few more words about the Calabi energy. First of all, one can restrict to considering Kähler metrics in a fixed Kähler class. What it means is fixing a Kähler metric and just considering Kähler metrics which are cohomologous to it. And now one can take the gradient flow of the Calabi energy restricted to this Kähler class, so that one has exactly this evolution equation. And what one ends up with when looking at the evolution of the associated Hermitian metric is the so-called Calabi flow, which was introduced by Calabi in 1992. Calabi introduced this flow in the hope that it would converge to an extremal Kähler metric, starting from a Kähler metric which was not extremal at the beginning. And this flow is a fourth order parabolic geometric flow. And in the compact case, many things have been proved. First of all, Calabi himself proved that the Calabi energy decreases along the Calabi flow. Then we have a short time existence and uniqueness result, a smoothing effect, which means that one can start from a non-smooth Kähler metric, and this flow makes this Kähler metric smooth as soon as the flow starts. Then we have a stability result for constant scalar curvature metrics, which means that if one starts close enough to a constant scalar curvature Kähler metric, then the Calabi flow exists for all times and eventually converges to a constant scalar curvature Kähler metric. And a recent result by Chen Chang is that the Calabi flow can be extending as long as the scalar curvature of its solution is uniformly bounded. Now, we have seen that the best kind of Hermitian metrics are Kähler metrics, but of course one is free to consider weaker conditions. For example, when the manifold one is considering cannot admit Kähler metrics. So, in this case, let Mj be a complex manifold, so we are also assuming that the almost complex structure is integrable, actually. And we will say that a Hermitian metric on it is balanced if its associated fundamental form is co-closed, or equivalently, if the 2n-2 form obtained by taking omega to the n-1 is closed. So, it is easy to see from this last formulation that Kähler implies balanced, so that this is in fact a generalization of the Kähler condition. One thing one might ask is if by taking a different power of omega, here one could have different generalizations of the Kähler condition, but the fact is that if omega to the k is closed for some k different from n-1, n, or 0, this automatically implies that the metric is scalar. So this balance condition is the only possible generalization of the Kähler condition in terms of powers of omega being closed. One can also easily see that if n is equal to 2, then balanced is equivalent to Kähler, since the exponent just becomes 1. We also have other characterizations in terms of different concepts. One of these characterizations is given by Goduchon, and is in terms of the behavior of the different Laplacian operators one can define on this Hermitian manifold. Another characterization was given in terms of positive currents by Michelson. And a consequence of the Balaxis condition is that every compact complex hypersurface of a complex manifold admits in balance metrics cannot be homologous to 0. There are many examples of manifolds admitting balance metrics. For example, twistor spaces of 4-dimensional oriented anti-self-dual Riemannian manifolds, as shown by Michelson. Then other examples follow from a result by Alessandrini and Bassanelli, who proved that the balance condition is stable under modifications. So, under maps such as blow-ups and blow-downs. If one starts from a Kähler manifold and performs a modification on it, one is not sure to obtain a Kähler manifold, but for sure one is going to obtain a manifold admitting balance metrics. Then other examples are given by left-invariant Hermitian metrics or unimodular complex Lie groups. Now that we have completed the part regarding preliminary notions, we can move on to describe the two geometric flows I have talked about in the introduction to this talk. The first one is the balance flow, which was introduced by Bedulny and Vezzoni, and which is a generalization of the Calabi flow. So first of all, we have to say a few things about the Calabi flow. We have seen the Calabi flow as a flow for our Hermitian metric in this way, but we can rewrite this flow in terms of the evolution of star omega, and this is given exactly by this flow where ρ is the Ricci form associated with omega. Now, we can generalize this flow in a very easy way by considering the Chern connection here. And now this flow preserves the closure of star omega, so that it preserves the balance condition. So one might think about considering this flow in the balance setting as well. But problems arise in this context, and the most important one is that this flow is no more parabolic. So what Bedulli and Vezzoni did was they simply added a term, this both-term Laplacian here, to try and fix this problem. This is the both-term Laplacian which was used, and this flow actually turned out to be a parabolic flow, and one can easily see that when the initial data is scalar, then this flow coincides exactly with the Calabi flow. So this is actually a generalization of the Calabi flow. In the compact case, Bedulli and Vezzoni proved a few results. One of these is short-time existence and uniqueness of solutions, and the stability of Ricci-flat calorimetrics. So, as we saw earlier in the context of the Calabi flow, we have in this case that if one starts close enough to a Ricci-flat calorimetric, then the balance flow exists for all times and converges to a point which is a stationary solution of the balance flow. So, after introducing the balance flow, I want to spend a few words about the anomaly flow. So, as we saw, the balance flow has its origins in the Calabi flow, which was created to find the spatial calorimetrics on a manifold. The anomaly flow comes from a totally different setting, which is not totally different because there are some intersections, as we will see, but it comes from string theory, which is a theory in physics. So I first have to spend a few words about this. So string theory is a theory which aims to unify general relativity and quantum mechanics, which are two theories in physics which operate at different levels of magnitudes and which are not very compatible one with the other. And the way the string theory does this is by modeling the space-time as a 10-dimensional manifold equipped with a principal bundle P. There have to be certain fields on this setup, a Riemannian metric on N, a dilaton, which is a smooth function on N, a 3-form on N, and a gauge connection on P, satisfying the equations of motion, the Bianchi identity, also known as the anomaly cancellation equation, which involves curvature terms on N and on P, and then the Killing spinor equations. So this setup is very, very difficult to solve, and so what Hall and Strominger did was to formulate an answer for the problem. So a way to simplify the problem in the hope of finding a solution. So in the answers by Hall and Strominger, N is assumed to be the product between R4 and a compact-oriented spin internal space of real dimension 6. The metric G0 is assumed to be the product metric between the metric of Minkowski spacetime and a certain metric on M. And the previous constraints, we're not including the equations of motions, but just the other two constraints can be formulated in this way, in this setup. So the manifold M has to be complex with vanishing Pernster class. In literature, these are known as Calabi-Yau manifolds. The fact that the first Chern class vanishes tells us that there exists a holomorphic 3-0 form which vanishes nowhere. Then we have to have a Hermitian metric on M with an associated Hermitian connection. We also need to have a holomorphic vector bundle E over M, which has a Hermitian metric on its fibers and a Hermitian connection with respect to this metric. The previous constraints now can be translated in this setting with the so-called Hall-Strominger system, which is made up of 3 points. The first one is the Hermitian-Yang-Mills condition for the connection on the holomorphic vector bundle. Then we need to have the conformally balanced condition, which was originally formulated in a different way as the so-called Di Latino equation. And then we need to have the Bianchi identity, which is formulated in this way. So one can easily see that some very special solutions can be obtained if we have a compact Ricci-flat Kähler manifold, and so by the Calabi-Yau theorem we have some solutions to this problem. But of course, one would like to have other kinds of solutions. But these proved to be very, very hard. The first non-Kähler solutions were found by Fu and Yau in 2008, so it's a very recent result. And so one other idea one could use is to see solutions as stationary solutions of a geometric flow, and hope that this flow converges to them in the same spirit as the Calabi flow we described earlier. So in this spirit, Fong, Picard, and Zhang introduced the anomaly flow in 2018. The anomaly flow is a geometric flow which takes place on a complex manifold of a complex dimension 3, having a fixed non-zero holomorphic 3-0 form and a holomorphic vector bundle E over it. And then the anomaly flow is a coupled geometric flow for a Hermitian metric on M and a Hermitian metric on the holomorphic vector bundle, which is formulated in this way. So we also need to choose a particular kind of Hermitian connection on M and a particular kind of Hermitian connection on E. And this is usually done by considering a certain fixed connection in the line of Gorushan we described earlier. An easy simplification one can consider is the setup in which one assumes the holomorphic vector bundle to be flat. So one assumes Ft to be equal to 0 for all t, and the anomaly flow simplifies as a flow for simply our Hermitian metric on our complex threefold. And this is in particular the kind of anomaly flow I considered in my work with Anna Fino. So here I've just rewritten the two formulations for the anomaly flow. One issue one has to be careful about is the fact that this flow is not always well defined. As a matter of fact, one has to ensure that the right-hand side is of type 2-2, so that both sides are of type 2-2, otherwise it wouldn't make sense. And this is always the case if one considers R and F to be the Chern connections associated with omega and H. In the compact case, when exactly R and F are the Chern connections, Fong, Picard, and Zhang proved the short-time existence and uniqueness of results, showing that the conformally balanced condition is preserved along the flow. They also showed a very important thing, that is that if the flow exists for all times, then the limit solves the Hallström system. And in this way, they were able to find a new proof of the existence of non-Kähler solutions, which had originally been formulated by Fu and Yau. The anomaly flow has been also studied in some special settings. For example, on complex unimodular Lie groups, which was again a work by Fong, Picard, and Zhang. Then it was recently studied on two-step nilpotent Lie groups by Puya and Ugarte. And our work is about the study of the anomaly flow in the context of almost abelian Lie groups. This seems like a nice point to end the first part of my talk, so I'll see you in the next part.